Hello, everyone, and welcome to another wonderful day of physical chemistry. So today we're going to be starting to build up the description of the behavior of gases. So we're going to be doing this by essentially combining two features, which is talking about how we can, how as physical chemists we traditionally build up models of our systems, and B, trying to apply this to how I can determine the pressure of a gas. And we're going to do this by building up what's called the kinetic gas model. So let's go ahead and get started by first of all talking about the general forms of physical models. So this is the classic form of how a physicist talks about a system. So the general approach for a physicist modeling a system, chemical or otherwise, is going to take one of two major paths. So the first one I often call the historic or the empirical path. So this is simply the idea that I start with a whole bunch of experimental data. I've usually collected this over a wide array of time, and I try and fit the system to some set of predictive variables. So I have some sort of response variable I care about and some sort of predictable variable I can control. First, I need to go ahead and identify which variables are going to be related. And then once I have these, try and connect these properties to some sort of mathematical form. We hope that it's linear. If it isn't, we may try and force it to be linear. Otherwise, we'll hope that it follows another simple form like an inverse relationship or an exponential model. And then turns out that a lot of these systems often provide a general good description of the system. The mathematical forms may occasionally get fairly complex, but the general failure of these sort of empirical models is that they tend to lack a good origin for why the model works. They end up being much more descriptive, and while occasionally predictive, they don't give you a good idea of why, which again, as a physical chemist, can occasionally drive me a little bit nuts. And so a good way to kind of look at how one builds up one of these empirical models is I'll tend to make a series of measurements, and then I'm going to fit these to some sort of simple model. And then I use this to build up a more general theory. And then what we try and do is test it against more measurements, see if it's a good general model or whether I have to add on some extra features. Turns out occasionally we're lucky and that a simple model works. Often, in order to make a model widely applicable, I have to add in a lot of corrections. And we're going to see this as a common theme as we go forward this semester. The other general approach is I'm going to start with a very simple system and some sort of basic set of physical rules that I hope the system follows. And I use this to build up a model kind of from first principles. So I often call this an ab initio or first principles model. So this is, again, ab initio is just Latin from saying more or less from first principles. So these are usually going to be very good at describing important features of the system. However, because we start with a simple system, you often need to add in constant correction factors to deal with the wider world. This leads to the classic joke that a physicist was asked to help a farmer whose cows weren't giving any milk. He took a look at the cows for a while and said, I have a solution, but it only works for spherical cows in a vacuum. And this tends to be kind of the problem with these models. They tend to work very good for simple systems, but by the time we get up to real systems, the number of correction factors you're adding can be quite cumbersome. But the big advantage of these systems is that they tend to be very good at attributing a physical origin to each of the terms, whether it's the original first simple model or the correction factors that we're adding in. So these can be quite satisfying once you get the hang of them. So a good general theme of how one of these first principles models work is you might do something like assume the existence of protons, neutrons, general nuclei, atoms, molecules, electrons, some sort of fundamental particle. Then what we do is we apply a series of either Newtonian or quantum mechanics, depending on what level your system is working, or if you get up to real physics, you might even start applying relativistic theory. Then once you've applied these basic set of theories, then what you can do is actually build a fairly good and descriptive model. And then you test against experimental results, figure out if there's any features that you missed, and then you might have to say, oh, I may have dealt well with the behavior of nucleons, but I may have forgot the behavior of electrons. Or I may have accounted for the existence of atom A, but not atom B. And so these can actually be, again, kind of tricky to deal with, but they often can be very satisfying. So let's go ahead and look how both of these physical models work in kind of a real system. So one of the best examples of an empirical model is our good old friend, the ideal gas law. Pressure times volume equals moles times gas constant times temperature. Beautiful system. And it turns out that we derived this in a very empirical approach, which is we made a whole bunch of measurements. So first, pressure versus volume for a whole bunch of gases, and we found a linear relationship in between pressure and the inverse of volume, and it was fairly general. Then we have pressure versus temperature. So again, this gives us Charles' law, again, a nice linear behavior, and the same thing with Avogadro's principle, linear behavior if I plot pressure versus number of moles in molecule. Again, these don't hold forever, but for most reasonable atmospheric conditions, they're pretty good. And so what you can do is say, wait a minute, I've got 3 linear relationships. I can go ahead and combine them together. I get my ideal gas law. I have a nice, simple description of the behavior of a system, but I have no idea what's driving the origin of these sort of behaviors. And again, later in the chapter, we'll start dealing with when this simple relationship breaks down, because we often need to add correction factors to our models, whether it's empirical or first principles. Now, one of the really cool things about physical chemistry is that you can usually derive the same exact set of equations from empirical or first principles. So let's try and derive the behavior of pressure from first principles for, again, an ideal gas. So we can rederive this same set of equations by making just a handful of key assumptions, and most of these you've probably heard about in general chemistry. But let's do a quick review. First, we're going to essentially follow the basic principles set out by Feynman. We're going to treat a gas as a set of molecules of a certain mass, m. Again, this is going to be the molecular mass, not the molar mass, so mass per molecule. They're essentially just ceaselessly moving, have constant translational motion. We're going to ignore rotational and vibrational. And generally, they obey Newtonian physics. So nice, simple system. So we're going to assume that in general, the diameter of the gas is going to be a lot smaller than the distance between particles. So because the size of the gas is relatively small, they're essentially acting as point particles that are going to be bouncing off of each other. And all of these interactions in between gases are going to just be elastic collisions. So this gives us classic billiard ball physics. I have 2 molecules that will come in, and the speed that they start on the collision is the speed that they end on collision. All that changed is who's moving in what direction. So we can use this to start describing our ideal gas system. Now, what we did empirically is we started by looking at pressure. And pressure is going to essentially originate from collisions with the container wall. Because how we measure pressure is, well, how often is a gas hitting either a pressure sensor or our container wall? So let's go ahead and look at collisions with the container wall. So we can use our good old friend Newtonian physics. I might be brushing off some old principles here. And it turns out that pressure is just simply given as the force of the collision per area the collision takes place over. So force, again, according to Newtonian physics, is going to be the change in momentum over the impact time, or the change in time. So this is going to be essentially, I do apologize for the multiple P's, essentially how much does the momentum of my gas change over a certain given time. So let's go ahead and kind of look at this a little bit more visually. So I'm going to have some sort of gas that's going to be coming in with um, a certain velocity. It's going to hit the container wall, and because it's an elastic collision, it's going to be bouncing back in the opposite direction. Vy and z won't change, but Vx is just going to be the opposite of what it started, going in the opposite direction. So this means that I can give my change in momentum as essentially twice my initial momentum. So I start with a momentum of mvx, and then I end with a momentum of negative mvx. So my momentum changed by essentially twice what I started with. So I took all that momentum, turned it in the other direction, thus giving me 2mv as my change in momentum. Where again, m is going to be the molecular mass, or the mass of a given molecule that's colliding with the wall. So this actually works out pretty well. I know that I can usually find the mass of my gas just by knowing what molecule is hitting the wall. Velocity we'll deal with later, but we run into a small issue. I'm not going to be looking so much at the pressure of a single molecule hitting the wall. I'm going to be dealing with something a little bit more messy. So I need to figure out how many molecules are going to be hitting the wall to get a good idea of the overall pressure, and not just the pressure from a single molecule. So when trying to figure out how many molecules are hitting the wall, what I can do is start by looking at a certain subsection of my wall with area A. And then I'm going to be counting the number of collisions with that area A simply by finding what volume of the gas is going to be, in general, colliding with the wall, and then using the density of that gas. And usually I can find the density of a gas from a series of measurements. So our density is essentially just going to be described as the number of molecules times the molecular mass divided by the volume. So that actually ends up being nice because it's going to more or less be the number of molecules that are hitting the wall. So what we can do is turn this, get a description of my volume that's going to depend on the velocity. So what it turns out is that the volume that's going to be hitting the wall is going to be related to the area times essentially how deep that area is. And it turns out that what I can do is describe this dimension of how far out a gas has to be before it'll hit the wall based on the velocity of that gas. So if my gas is moving fast, this volume is going to be quite big. If the gas is moving slow, this volume is going to be relatively small. And then it's going to also depend on what sort of time interval I'm dealing with. So the volume that's going to hit the gas is more or less going to be related to the absolute value of the velocity, because it's hard to know which direction they're moving, times the time. But because half of my velocity will be positive and half will be negative, I go ahead and I use that division by 2 to help cancel out that negative feature. So that lets me use these absolute values, which will be very useful later. So what I can do is take all the equations I just derived, put them together, and I'll get a much more simple form, because it turns out that cancellation of variables is an amazing thing. So my pressure is given as the force over the area. But again, my force is going to be the change in pressure over the change in time. And then what I can do is insert my change in pressure as twice mv, and I get a fairly simple overall pressure equation, which is related to the mass of the gas, the velocity of the gas, the area, and the time interval I'm measuring over. So what we can then do is try and determine the number of collisions that are going to give this pressure by, again, using my density times my volume. So we're going to then input the equation we had for our density, which is right here. We're going to essentially ignore the corrected volume term for now. You'll see why later. And then we'll also insert our volume equation of Vx times delta T over A. And then we have that factor of 2 that shows up. Again, it's worth noting that implicitly I'm looking at the absolute value of the velocity term here, but I omitted that for sake of clarity. So what we can then do is go ahead and combine these equations to give an overall pressure, which simplifies when I account for the number of collisions occurring times the pressure per collision. We see another number of nice, we can multiply all of our factors here together, and we get a lot of fairly nice cancellations, including my 2 areas will end up canceling out. My 2 time intervals also end up canceling out. My factors of 2 also end up disappearing. And I can go ahead and collect my mass times Avogadro's number times the number of molecule times the number of atoms into a much nicer number of moles, into a nice kind of convenient feature. Where now what I have is my pressure is going to depend upon the molecular weight of the gas I'm dealing with, the number of moles of my gas, the volume of the system, and the square of the velocity just in the x direction. So all that's going to be related to pressure. But we only have one term here on the bottom. That's going to be our volume. So we can move it over to the other side. And this should hopefully start looking familiar. I now have some descriptor of pressure times volume that's going to depend upon the velocity of the gas as my only real variable, because the number of moles and the molecular weight are going to be a little bit more fixed. So what this ends up doing is giving us a real descriptor. Now we have to figure, we now find that the pressure of the system is going to be highly dependent upon the average velocity of our system. So now we have to figure out the average velocity of a gas. And it turns out that this actually can be a little bit tricky. So I'm going to go ahead and give that its whole a lecture of its own next time, of where we can try and use some more atomic level descriptors to figure out how fast a gas tends to move. Till then, take care.